So in this example, we'll see the example of AND gate. We can see the truth table here. Source A, source B, two sources have taken. The AND gate says that if any one source is 0, then the result is 0. Okay, result is 1 only when both the sources are 1. Okay, so that makes the AND gate truth table. We are going to see realization. Okay, we'll see the realization in which I have got, this was about an AND gate. Let me open the AND gate. We can see two push buttons. I have to close both the push buttons to generate or to take this drill motor to on. So let me close one push button. I see it is this indicator is on. I close the second push button, and then I see that this particular drill motor is on, green. So I have to close both the push buttons to put this drill motor on. If I release any one input, I see that the drill motor is put off. So let us make this realization into the ladder. For the ladder, we have to again open the WPL soft, that is the programming software, and let us write a ladder for them. In the ladder, I take X0, I can give a command as push button 1. I can take X1 as open contact, and I can say push button 2. And this makes my AND gate. So let us say the output Y0 or Y1, I can take any output and say drill motor. Let me download this program. We see that I have to close both the inputs to generate output. And when I compare it with the electrical system, these two inputs comes in series. Okay, so when I close both the inputs X0 and X1, I see that Y0 turns on, and on the system here, we are going to see that when I close X0, it is green. On the ladder also you can see, and when I close X1, okay, I see that indicator Y0 is on. This is our drill motor we have considered. So when I close X0 and X1, output is on. If I release any one input, output is off, either this or this. So this makes the AND gate. After this, we'll see the example of NAND gate. This is the truth table of the NAND gate. We see that it's a not AND if both the sources are 0, 0, output is 1. Okay, only when both the sources are on, the output is 0. Completely opposite of the AND gate. Not AND, is NAND. After this, we will see realization. I have got one system in which this indicator, which you see here, turns on in multiple conditions. Like for example, we can see a sensor here, and let us say this is the object. So this is the object sensor. This particular sensor is going to sense the door, whether open or closed. So we can say it has a door switch or a door sensor. Now this indicator is currently off because the object is placed as well as door is also closed. Now when the indicator turns on, I want like this. Whenever the object is not placed, say I'm removing the object from the object sensor, I see that indicator is on. I place the object, but I do not close the door. So I open the door. The moment I open the door, indicator is on. Also, if I am not placing the object and door is also open, indicator is on. Then when the indicator should be off, the object must be placed in front of the sensor as well as door must be closed properly. Only then indicator is off. So this is the example of the NAND gate. We are not dealing with the start and stop of the motor, but we are just checking for the indicator. So these are the two digital input, object sensor as well as door switch, and we will write a ladder for that, saying the NAND gate. Let us consider X0 and X1 as the door switch and the object sensor. So let me delete this particular thing. Then let me take the X0. Let me say door switch as a comment. Sorry, this should not be open content because hardware is open. So let me take as a normally closed content because we are going to see the NAND gate, or with other normally closed X1 same object sensing. So this makes my NAND gate. Let me all this and show the output. That could be my indicator. Yes, so this becomes my NAND gate. If I am not closing the door, indicator will turn on. I am not placing the object, indicator will turn on. I am placing the object, but door is open, indicator is turned on. Indicator will be off only when both the conditions are satisfied. That means object is also placed properly in front of the sensor, as well as door is also closed. That moment indicator will be off. So let us download this program. Yes, I see that here indicator directly turns on because we have considered this as a door switch. It is open currently, that means door is open, object is also not placed, indicator is on. Let me place the object in front of the sensor. The moment sensor detects the object, let us consider that object is placed. But since door is open, indicator is on. Let me close the door. Let us say I am closing the door, indicator is off. Now object is also placed and door is also closed. So indicator is off. If I remove the object, indicator is on. Or if I open the door, indicator is on. Or if I am not placing the object as well as door is open, indicator is on. So this was the example of the NAND gate. After this, we'll see the example of the run, stop, and jog program. Jog is also called as pinching. It is momented on. I have got one system in which I have shown a cutter, then I have shown a tube or the wire, and my job is to cut the wire at the marking. I have a control panel. On the panel, I can see run, stop, and jog. When the operator says run, the output is continuously on. This motor is going to draw the tube or the wire towards the cutter, and it is continuously on even if the run is released. That means it is latch. Operator will say stop whenever he wants to say stop. The wire or tube remains at that position, and then he will simply say jog. He will press and release the input so that this wire moves towards the cutter, and that action is also called as pinching. Jog is used to gain accuracy. So let us find this. I say I press and release run. I see that wire is continuously moving. When it approaches near the cutter, operator says stop. Motor is put off. And now I will simply say jog. I press and release the input. I see that motor runs when I press the jog, motor is off when I release the jog. So that I can gain accuracy and I can exactly take the tube, the marking of the tube down the cutter. So this was the example of the run stop jog. Let us do this while writing the letter. So let me write here the program run stop and jog. I am going to take one input x0. Let us use the command as run. To do this program, I am going to use a memory bit. Memory bit are also called as auxiliary input or the dummy IO points. Let me latch this memory bit with the input. These memory bits are internally present to the CPU. You cannot connect any hardware like the sensor or the switches or the relays to this memory point because they are not seen outside. Let me take the open content of the memory bit here and show the output which I want to generate. Let us say motor as Y0. And for jog application, I am simply taking a parallel contact with that of memory bit N0, and I am labeling it as X2 and saying it as job. Stop, let me take it here as X1. Let me call this as a stop. So this becomes my run, stop, and job program. Let us download this program and see the working. In this case, X0 is a run, X1 is a stop, and X2 is a job. So let's see how it works. So this X1 is a run, sorry, X0 is a run, X1 is a stop, and X2 is a job. Why not? Is a motor. So let me press and release. I see that output is continuously on, so motor is continuously running. Let us consider that it is drawing the wire continuously. When it approaches near the cutter, operator will simply say stop, output is off. Okay, wire is hold, and now we will simply say job. We will press and release. Presses and releases. Okay. So what happens is that it gives a inching effect, and I can easily take the marking of the wire near the cutter. So it's continuously on, stop is off, and job is also called as inching. So using the memory bit, this becomes very easy to write a program. After this, we'll see the realization of the timer. I have taken one slide here in which I have shown a motor, a control panel with a start and stop, a PLC. Then even there is a time delay in seconds. The application is operator says start. After 10 seconds of the delay, this motor turns on. So let us see. I press the start. I see that timer start, and at the 10th second, the motor will turn on. Okay. When the operator says stop, motor is off. So this was the time delay, on delay timer. Timer are used to cause a delay. If I don't want to generate the output instantly, but I want to wait for some time, I use a on delay timer. So let us write the same thing in ladder. So let us delete these previous things, and we'll use a segment command saying on delay timer. They are used to cause a delay. Let me take an input X0. It's always better to use a memory bit as a power bit. When we are dealing with a timer, we have to use a memory bit. Let me latch the memory bit. This is also called as power bit. On this N0, let me take the timer. Now the timer, we can simply type using the keyboard TMR, and it is not a case sensitive. We can take a small or uppercase. So TMR P0 is the first timer address. Suppose if I want a 10-second delay, I have to use 100 with the letter K. K stands for constant for this WPLSoft, and I have to use 100. 100 stands for 10 seconds. The time base or the least count is 100 millisecond. Okay, or 0.1 second, and then we have to use 100 as a multiplication constant. So 100 into 0.1 will give us 10-second delay. The unit will be in seconds. So let us say okay. Every timer generates a done bit. So let me say, take the done bit address as P0 and say the command as done bit. This is the bit which is generated at the 10th second, and I can show the output y, let's say 1. Same as motor. Let me put one stop here. As normally close contact. Then I am going to download this program. In this example, I am generating the output after 10 seconds of delay. So you see that I am going to close X0. Memory bit will turn on. It will power up the timer T0. That will run for 10 seconds. At the 10th second, this bit will become green and it will generate output Y1. When I say stop, everything is cut off. The memory bit will be off. Timer will go back to 0. So let us see on the screen. I press here X0 and then I wait for 10 seconds. On the ladder, the timer has started from 50, 60, it will go to 100. The moment it reaches 100, we see that this particular output turns on at a 10 second. When I use this X1, output is off. So then you will see, I just press and release X0 and then I wait for 10 seconds. At a 10 second, that Y1 will turn on. It has turned on. When I say X1, I'm putting the memory bit off and everything will go off. So I press it. The timer goes back to 0. While running, if the timer is running, if I say stop, at that moment, timer will go back to 0. So I press X0. I see the timer runs 2 seconds, 3 seconds. I press X1. I see that timer goes back to 0. Timers are used in many applications. Even there are multiple types of timers like off-delay timer, retentive timers. We will solve some more examples based on timers. In the second example of the timer, we have shown one slide in which there are two motors or the two machines and both have the timing effect. When I say start, this motor runs for 10 seconds. After 10 seconds, this motor is put off and the second machine or the second motor runs. And this motor also runs for other 10 seconds. So let us see. I press the start. I see that motor turns on and the timer is going towards the 10th second. At the 10th second, this will be off and this will be turned on and timer for that will again start automatically. At the 10th second, this motor will be off. I can say stop to reset everything so that again I can start. So we are going to see a ladder for this. So to check the ladder, let me delete this. In this example, I have to take two timers. So first of all, it's always a good idea to take the memory bit as a power bit. So I'm taking the memory bit, batch it. Even we can use the shortcut keys for using everything. On the memory bit, let me take the first timer. Or even I can show the output as Y0, saying motor 1. Give the command. Simultaneously, let me put the timer on. Again, I can simply type using the keyboard TMR, let us say T1 with K 100. Again 100 because I want a delay of 10 seconds. After 10 seconds, I want to put up this Y0. So what I do is that I place a normally closed contact here just before this Y0 with the address of this done bit T1. So let me take the T1. I have to properly use T1 because the timer itself is T1. I cannot take T0 because it is not used. Let me say done bit 1. So this is almost a 50% of the program. Let me take the same done bit T1 as open contact to write the entire program. Show the output Y1, say motor 2. Similarly, I have to take a timer, other timer, let us say T2 with the same time, 10 seconds. The way I put this Y0 off using the done bit in a similar fashion, I have to use a done bit here to put off the Y1. So done bit of the second timer, that is a T2. So let me say done bit 2. I'll check if I have taken a stop. So I have not taken a stop. Let me take X1, normally close contact as a stop. So I can stop the entire thing whenever it is required. Now let us see this program. What we are going to do is that we will download it and we'll check it on the actual system. When the operator says start, the first motor is put on for 10 seconds and the second motor is also put on for next 10 seconds. So let us check over here. This is my X0 start, motor 1 and motor 2. This runs for 10 seconds. After 10 seconds, this will go off automatically and it will start this motor on. So let us see this. I see that this motor runs even on the ladder. We see the timer is moving. 10 seconds, this will turn on automatically. Even the second motor, that will also remain on for 10 seconds. See, after 10 seconds, it is put off.